review also that we don't have class on Friday, Monday, stoichiometry test. We will have a short mini quiz today at the end of the class, which we're anticipating going to take about 10 minutes. I anticipate giving you more time than that to take it. The review has nothing new. It's just a quick summary of everything that we've already done. So I'm going to go relatively quickly. If you have questions along the way, please ask. But there's some simple voice. Take the earbuds out. Can you hear me better, Mitchell? Thanks. Simple examples, basic stuff, just to reinforce the main concepts. So hopefully it'll go fairly quickly and everything will seem okay. It's weird.
No chemistry.
Oh, no chemistry today. All over those yesterday.
I showed that.
I woke up
Answer him. It's probably not him.
Good job. All right, let's hear it for Mr. Gusway.
I was actually.
Oh, yeah. All right, back on track. So here's what we're going to cover. We're going to cover ratios. We're going to relate our ratios to bikes. Like there's a dog riding a bike. That's pretty neat. Mole conversions, basic stuff. Stoichiometry, we'll do mass to mass. That'll be the longest road on our little stoichiometry map. Limiting reagent or limiting reactant, whether you say limiting reagent or limiting reactant, it means the same thing. And percent yield. So terms, honestly, you should already know these. If you want to jot them down again, that's fine. But stoichiometry is the mass-to-mass relationships in chemical reactions. When we talk about mole-to-mole ratios, we're talking about the coefficients in our balanced chemical equation. So that's the numerical relationship between the different substances in the chemical reaction. So for your rocket lab, your mole-to-mole ratio was 2H2. So you need 2 moles of hydrogen gas for every 1 mole of oxygen gas to produce 2 moles of water. Your excess reactant, oftentimes in a problem it'll say, how much of this can you produce with this much of that, and something else is in excess. That simply means that you don't have to worry about that stuff running out. And then finally, the limiting reactant is going to be the first one to be used up in the reaction. I know you had percent yield there also on that sheet. I'll give you a definition for that a little bit later. I don't have it on this slide. So if your limiting reactant is the one that gets used up first, that's going to be the one that limits how much you can make of your product, or it's going to be the one that prevents you from making more of your product because you ran out of the stuff that you need to use to make the product. So first, ratios. We did recipes early for the first day with the worksheet on, I don't remember what the first recipe was, cookies or something, and then we had ferocious fruit salad. We did the Lego activity, so this is the same deal. So this is bikes. We got frames, handlebars, and tires. So we're just going to assume, very basically, very simply, that to make a bike, you gotta have 2 tires, 1 frame, 1 handlebar. So how many do you need to make 3 bikes? We're gonna start with 3 bikes and figure out how many tires do we need. Well, we know that we need 2 tires to make 1 bike. So we're gonna write that as a fraction. 3 bikes times 2 tires per bike. Our bikes cancel out, we're left with tires. Plug and chug, 3 times 2 gives you 6 tires. That is super simple. So I'm not trying to challenge you here mathematically. Also, how many frames do we need? Well, we need 3 bikes and we need 1 frame per bike. So we're going to need 3 frames. And I'm not going to show you the calculation for the handlebars. I think you got it. I didn't even provide you a space for it, but it's exactly the same, except that here we'd have 1 handlebar per bike, and we'd have 3 handlebars. So same question, but slightly different spin. How many bikes could we make if we had 6 tires and 4 frames? Again, I realize you can do this math in your head. Just to reinforce the process. For our limiting reactant product, we are going to do 2 calculations. For all your limiting reactant products or limiting reactant problems, you're going to be told 2 givens. You've got this much of one thing and this much of another thing. How much can you make? So you're going to do the same calculation twice, and then you're simply going to take the smaller number. So we got 6 tires. We use our relationship for 2 tires per bike to figure out that we can make 3 bikes with our 6 tires. And clearly we can make 4 bikes with 4 frames. But since we only have enough to make 3 bikes with our tires, that's going to be our limiting reactant or our limiting component in our bike building process. That's easy, right?
Yeah.
Good, we just keep going then. I don't have any place for you to take notes on this. This is just reviewing very basic concept. In our rocket lab, the recipe for the water was our balanced chemical equation. 2 hydrogens, 1 oxygen gives us the ability to make 2 waters. So that's how we interpret our recipe, our balanced chemical equation. We're looking at the coefficients to say that we need 2 of these and 1 of these to make 2 of those. That's all that's saying. On a small scale, we can talk about atoms or molecules. On a larger scale, we're going to talk about moles. That's what we've been talking about, larger scale. But it's the same ratio. So the balanced chemical equation tells you how much of each piece you need to make what you want. So a couple of simple examples here. Again, I don't have a spot for notes here. This is just stuff that you should know. The coefficients of the balanced chemical equation are what give you your mole-to-mole ratios. That tells you that you need 2 hydrogens for every 1 oxygen, or 2 hydrogens to produce every 2 waters. Those are your givens and your gets. If you know this, can you find that? And you can do that between any 2 substances in your chemical equation. So you can do it between reactants, hydrogen and oxygen, between a reactant and a product, oxygen and water, or if you have more than 1 product, you could do a mole ratio between products. In our rocket lab, we only had the 1 product, the water, but in a lot of your chemical reactions, of course, you've got 2 products, but you can do a mole-to-mole ratio between the products as well. So here's some simple examples for our water. Between our reactants, we've got 2 moles of hydrogen for every 1 mole of oxygen. Between our reactants and our products is a 2-to-2 ratio. between the water and the hydrogen. And we could certainly write another one that is a 1-to-2 ratio between the oxygen and the water. Just to the left of that, yeah, I guess bottom left are some more. Simply asking you to write your mole-to-mole ratio between the reactants. Well, our reactants are the iron oxide and the carbon monoxide. So you can write 3 moles of carbon monoxide over 1 mole of your iron oxide. Or, what's the other one we could write? I'm sorry? Well, we could do that also, which we'll do in a moment, but just between the reactants, all I'm asking is that this doesn't have to be in this form. It can be 3 moles of carbon monoxide over 1 mole of iron oxide, or it could be 1 mole of iron oxide over 3 moles of carbon monoxide. It simply depends on what you're given in the problem and what you're solving for. Mole-to-mole ratio between the iron and the carbon monoxide. So this is what Emily was just referring to, so we can, oh, these are our products actually, iron and carbon monoxide. So we got a product and a reactant. So if we write that, it's either going to be 3 over 2 or 2 over 3. So we got to make sure that when we're doing these conversions in our T-charts, that, and this is where a lot of you are a little bit rebellious or a little bit resistant, got to make sure that you include your formulas or your chemical symbols in your steps so that you can keep track of what is canceling out, because we're moving from one substance to another in all these problems, as opposed to before when we were doing mole-to-mole or mass-to-mole relationships. We were starting out with, say, this much mass of magnesium. We're converting into moles of magnesium, so it's always the same stuff. Here we've got to keep track of our formulas so we know which substance we're talking about. And then finally, the mole-to-mole ratio between the products. We've got iron and carbon dioxide. So it's either going to be 3 moles of carbon dioxide over 2 moles of iron, or flip it, and you'll have 2 moles of iron over 3 moles of carbon dioxide. And again, the form of that fraction that you're going to use, that conversion factor, is simply dependent on what the problem's asking you to solve for, what needs to be canceled. Okay, from here, let's use our mole-to-mole ratios to figure out how much of a reactant is consumed, and then we'll do a second problem to figure out how much product is produced. So in the first one, this is how many moles of carbon monoxide, how much of this stuff is going to be used up if 12 moles of iron is produced. You're not going to need a calculator for this, but we're just going to show you how to set it up. So we're always going to start, well, what you really should be doing is probably underlining what's given in the problem. So I put a little line under 12 moles of iron and recognize that this is what I'm hunting for. Or maybe you write 12 moles right under your iron. And then carbon monoxide is what we're hunting for. How much of that do we need to use? So we're going to start with our 12 moles of iron. Our mole-to-mole relationship between carbon monoxide and iron is 3 to 2. That's from our balanced chemical equation. We cancel our moles of iron, plug and chug, and we've got 18 moles of carbon monoxide that's being consumed.
On the test, will we have to do a T-chart anymore? You can do it here, or like, you know what I'm saying?
I guess if that's asked you to show work, yes.
Okay.
She just asked on the test if you'd have to show a T-chart. The answer is Probably, yes. If it's some sort of a story problem, you're going to want to show your work. Please recognize that, and we all recognize that we can certainly do this in our head. But if it's a story problem and you're being graded on your work, then the more you show, the better off you are. All right, second half of this problem. Now we figured out how much stuff we're going to use up. Next question, how much stuff can we produce? So again, we're looking at what's given. We want to know how many moles of carbon dioxide can we produce. That's this guy. If we have 4 moles of iron 3 oxide. So we're starting with 4 moles of our Fe2O3, and we want to convert that into moles of carbon dioxide. Always start your T-chart with what's given. So we're going to start with 4 moles of iron oxide. We use our mole-to-mole relationship, 3 to 1. Iron oxide has to cancel, and this, what I said, it only depends on what the problem is asking, whether this is going to be 3 moles of carbon dioxide over 1 mole of iron oxide, or vice versa. So we want to go from iron to carbon, so our iron oxide goes on the bottom. Cancel our iron oxide, and we've got 12 moles of CO2 as our final answer. I would anticipate that your worksheets and your test questions are going to be a little more numerically challenging. And these are just very basic problems that we can do in our head in terms of the numbers. But you may be given 4.63 moles of something instead of just 4 moles. All right, so we're already done the front side. Flip that bad boy over. Longest road you're going to have to travel is the bridge from mole to mole. So you got this little diagram. We talked about this last week as well. The longest path you're going to have to go is from mass of one substance to moles of that substance, and then mole to mole, which is what we just did. And then finally, moles to mass. Oh, we certainly could do particles, yeah, but it's not going to make the map any longer. So we could go from particles to moles, and moles to moles, and then moles to particles. Either way, it's going to be 3 steps. Will be your maximum size T-chart. All right, so let's go back to hydrogen and oxygen. Like in the rocket lab, want to know how many grams of oxygen are going to be used up if we completely combust 6.86 grams of hydrogen. If this was given in words, if it said how many grams of oxygen gas are consumed in the combustion of 6.86 grams of hydrogen gas, please make sure you recognize your diatomics, that it would have to be H2 and O2. I'm giving it to you in this question, but you should be able to, need to be able to identify your diatomics and read a problem and write your own chemical equation. For most of these, I've given you the chemical equations. So, we're going to start with our 6.86 grams of hydrogen. That's going to be the beginning of our T-chart. You just have a line there. I didn't indicate how many steps, but you can certainly figure that out as we go along. We want to go from, if we go back to our map, we're going to go from mass of hydrogen to moles of hydrogen, moles of hydrogen to moles of oxygen, and then finally moles of oxygen to grams of oxygen. So we start out with our 6.86 grams of hydrogen. For every 1 mole of hydrogen, there's 2 grams. A little more precisely, 2.02, but a number of you have asked about how many digits do you need to carry out in your calculations. When we were doing the plane crash activity and the empirical formulas and all that, it was really imperative that we kept a lot of extra digits so that your numbers worked out, because we had to find that least common denominator and multiply by something to get all of our numbers to work out to whole numbers. Here it's not going to be quite so important that you write out a bunch of extra digits in your molar masses. So once we converted our hydrogen into moles of hydrogen, the next step converts moles of hydrogen into moles of oxygen. And the last step converts our moles of oxygen into mass of oxygen. And then finally our answer is 54.9. One thing that I do want to point out is that when you write down your final answer, your significant figures should match what's given in the problem. So if we're given 3 sig figs in our known, our final answer should be rounded to 3 sig figs. And it doesn't matter how many significant figures are in our conversions. We're assuming that these are exact. So if you have 3 digits at the end, you do your plug and chug, whether you write 2.02 or 2 grams per mole, you're still going to round your final answer to the same number of digits that you started with. Okay, so what do we do? We balance the chemical equation. Well, you didn't have to balance it this time, but if you were given a description of the chemical equation, you have to write it out. Make sure you balance it. Clearly indicate or clearly note what's given and what you're hunting for. What's the given and what's the get. What's your known, what's your unknown. Check out your roadmap. Roll grams to moles, moles to moles, moles to grams. Write your T-chart out. Show your work. Cancel your units. Again, make sure that you keep the identity of your units. And then finally, as I just mentioned, round your final answer to the correct number of significant figures. Okay, next we got limiting reagent or limiting reactant. So this slide simply reminds you what we talked about earlier with our bikes. Exactly the same stuff as we did in that second problem with the bikes. We end up with 3 bikes produced from our tires. We could make 4 bikes from our frames and handlebars, but we're limited to only 3 bikes because of our tires. So for each of these limiting reactant problems, you're given 2 known values. You're going to calculate the amount you can produce from each of those known values, and then you're going to compare your answers and choose the smallest answer. That smallest result is the most that you can produce because you're limited to that amount from your givens. So in this case, 3 bikes is all we can get. So when we find the limiting reactant in chemical equation, it's the same deal, except that instead of dealing with bikes and handlebars, or tires and handlebars, we're going to be dealing with hydrogen or carbon dioxide or whatever other substance we're dealing with. So the limiting reactant is the reactant that's completely used up. It's the one that limits how much you can produce. To calculate or find your limiting reactant, you're going to calculate twice. How much can we produce? And then you're going to select your smallest answer. So both reactants are given. Whenever you see 2 givens in a problem, that is a big red flag or clue that you're dealing with a limiting reactant problem. You're going to convert each of them to the same product. And then you're going to choose your smallest answer. The smallest answer tells you how much you can produce. The starting point of that smallest answer on your T-chart tells you what your limiting reactant is. So we got an example for you. We've got methane, oxygen forming carbon dioxide and water. So this is a combustion reaction. If we got 12 grams of CH4 and 30 grams of oxygen, how many grams of carbon dioxide can we form? So we're going to do two T-charts. One, we're going to start with 12 grams of methane. We're starting with 12. When we do our molar mass for methane, carbon has a mass of 12. 4 hydrogens give us another 4 more, so it's 16 grams per mole. From our chemical equation, our CH4, our methane, has a 1 in front of it. And our carbon dioxide has, carbon dioxide has a 1 in front of it. So it's a 1-to-1 ratio. Then finally, we're going to convert that moles of carbon dioxide into grams of carbon dioxide, and you'll see that we get 33 grams. 3 sig figs here, 3 sig figs here. Even though when you plug that in your calculator, it comes out to be just 33. You don't get 33.000 or anything, but you should keep 3 significant figures. When we do the next one, our oxygen, same steps, except the first couple of steps, but our last step is always going to be the same. 44 grams per mole of carbon dioxide. Well, we're going to go from mass of oxygen to moles of oxygen to moles of carbon dioxide, and then finally moles of carbon dioxide to mass of carbon dioxide. Our smaller answer is 20.6. So please circle it. Circle your smallest answer when you do these. The fact that this is circled tells us that oxygen, what we started with, is our limiting reactant. That's going to be what runs out first. We're still going to have leftover methane in this reaction that never gets used up because it doesn't have anything to react with anymore. Any questions so far? Again, this is ideally all stuff that you're pretty comfortable with and pretty familiar with. So again, we balance the chemical equation, underline 2 givens, and identify what you're solving for. Do 2 T-charts, 1 for each of them. Circle your smaller product and indicate what your limiting reactant was. And we're almost done. All we got left is percent yield. With percent yield, we've got 3 different terms that we're dealing with. The theoretical yield, or the ideal yield, is how much you would produce if everything in life was perfect. So up to this point, whenever we've done our calculations, our T-charts, like in the previous problem, we're assuming that we're producing, that we're getting 100% yield, that we're producing as much as we could possibly produce. The actual yield is more your dose of reality. This is what actually is produced. And then the percent yield, of course, is just that, a percentage So we're going to take the part, which is our actual, and divide it by the whole, which is our theoretical or our ideal, and then multiply it by 100 to get it into percent form. So the equation for calculating percent yield is simply actual over theoretical times 100. Sorry, too fast? Too fast, my bad.
Always have a calculator.
You're allowed to have one.
Do you have an extra? Mine's broke in the cold weather.
Really?
Yeah, the screen just cracked.
Huh.
And then it started leaking ink or whatever's inside now. My calculator.
Yeah, I don't think it's ink.
Yeah, it's probably not ink, but it's something that's purplish.
Alrighty. So we got one last problem to do. Here's our equation for percent yield. So we want to find the percent yield in this chemical reaction. We have calcium carbonate that's going to decompose into calcium oxide and carbon dioxide. Want to find what the percent yield is if we produce 6.81 grams from 20.7 grams of our reactant. So the first thing we do is the same stuff we've been doing. We're going to take our 20.7 grams of calcium carbonate. That's our starting point, and we want to figure out how much should or would we expect to produce in terms of our carbon dioxide. So we start with our 20.7, do our mass to mole conversion, and then our mole to mole conversion to get from calcium carbonate to calcium oxide. And this tells us that if everything was peachy, everything was hunky-dory, everything was perfect, bless you, we would form 11.6 grams from 20.7 grams. That would be your ideal case. That's your theoretical yield. Then we're going to compare this answer to what it tells us we actually did produce, 6.81, which is our actual yield. So our percent yield is actual over theoretical, which in this case is 6.81, divided by 11.6. So the 6.81 is our actual. Your actual amount produced is always going to be less than your theoretical. Your theoretical would be 100%. Whoop. All right, stop doing that. So we take that ratio, multiply it by 100, 58.7 is your percent yield. Any questions on anything we just did? Anything that looks unfamiliar? Okay. Then it's over. But we're not done.
When you start notes on this, when you start notes,
No, but you can't pull out that orange sheet, your little survival guide, and calculator. If you have a
Mr.
calculator.
Kelleher, you can turn off the
Anybody have an extra calculator? Mr. Gussie?